Today we're going to learn about the intuition behind root mean squared error, which is the common loss function and evaluation metric used in regression problems. So as a review, regression is when you're trying to predict a continuous value in machine learning, let's say the price of a house or the average score on an exam or things like that. So if you're trying to predict a continuous value, then ideally, the thing that your classifier predicts is going to be as close as possible to the true value. So the symbol we use in math, here we see the equation for root mean squared error, or RMSE for short. So this y with a hat over it, that is the predicted value for the ith data point. So we have n data points total, and we can index them with I, just like in a for loop, for I in range of whatever. So y hat sub I is the ith predicted value of the classifier, and y sub I without the hat is the true value of that data point. And so what we have in this equation here is we take the difference between the predicted value and the true value, and we square it. We'll talk about why we square it in a second, but we square it, and then we sum up all of these differences of squares and essentially take the average. So this equation here is really a mean. It's the mean in the RMSE, because you sum everything and then you divide by the total number of samples. So it looks like maybe a complicated equation potentially, but it's not. It's just, this is just the average. And what are you averaging? You're averaging the difference between the true value and the predicted value squared for all data points. So let's first think about the intuition for this without the squared. So if we didn't have the squared thing here, then we'd be, and let's ignore the square root as well for now. So if we didn't have the square and we didn't have the square root, then this is just the average of the differences. And if the differences between the predicted and the true value are large consistently, then you're going to have a high mean error, and that's called a mean absolute error. And if your classifier is correctly predicting or getting close to the right number for all the data points, then this mean absolute error is going to be low. So that's why it's a good loss function, because we want to train our regression model, our machine learning model, to predict as close to the true value as possible. So if we're optimizing for minimizing the difference between the predicted value and the true value for all data points, then that's good. We'll have a good model. Okay, so what about this squared term here? Why do we not term, but why do we square the difference? The reason is twofold. Firstly, let's say that we didn't square. Well, then we would have to take the absolute value, that difference between them, because if, let's say on average, it's predicting off, but it's predicting both higher than the expected value and lower than the expected value, then if the error was very large for all data points, but it's about evenly over predicting and under predicting, then the mean error is going to be 0, which is misleading because it's mispredicting everything. So instead, if we square it, then it doesn't matter if you are subtracting which one you're subtracting from what. You could subtract the true value from the predicted or the predicted from the true. It doesn't quite matter. But we could just do absolute value. So why do we square it? Well, we square it because we want to penalize increasingly larger differences. So like, that if the difference was 2 squared is 4. If the difference is 3 squared is 9. 9 is a much higher penalization than 4, even though 3 is kind of only a little bit larger than 2. So by squaring it, we're penalizing larger values much more. And yeah, so that's basically the intuition between mean squared error. We can add root to it to kind of undo the effect of the square, and what we're doing in that case is kind of having something similar to the distance formula. So if you take the square root of the sum of a bunch of squares, it's analogous to the distance formula. Okay, so how do we code this in this problem? Well, so in this coding problem on MLPro, which you can go to on mlpro.io/problem/RMSE, the goal is given a list of true values and a list of corresponding predicted values. Can we calculate the root mean squared error? So to code this, let's first calculate the sum of the differences of the squares. So we can maybe make a variable called squared differences sum, just to be descriptive. We'll initialize that to 0. Then we want to loop through all of the values in both lists. Since they're the same length, we can either use range of length of true or range of length of predicted, it doesn't matter. And as we loop through, we just want to add to the squared differences sum. So add the square of the ith true value minus the ith predicted value. So that's all we need for getting the squared sum of the differences. And we want to then take the square root and make it an average, so we can return the square root of the squared differences sum divided by the total number of points, which we could either do as length of true or length of predicted. Just to change things up, I'll say length of predicted. And that should give us our true answer, our root mean squared error. So let's see if it works. I'm hitting run code. And yay, it worked. So that's root mean squared error for you. If you have more questions about it, feel free to leave a comment and I'll respond. And definitely check out the problem on MLPro.